School of Business, and hopefully you'll tell us about some cool stuff covering block structure activation.
Thanks. So today I'm going to tell you about the work I've done here with Shibi, who is at Berkeley now, Alessandro and Arti. And I'll talk about recovering block-structured activations. So the problem with modern data is that we are getting more and more of it. And it's a question, how do we make sense of such large quantities of information? In particular, the problem is that the sensors are collecting more and more attributes, and we have a large collection of noisy attributes that are being collected for each object. This problem arises in computational biology, where we're connecting information about a large number of SNPs in human genotype. In astronomy, we have high-dimensional, we have very intricate information about the sky. And so in neuroscience, we have a large number of voxels that we need to deal with. And the question is, how can we make any sense out of this very complex data? So what we are going to exploit is that often there's some underlying low-dimensional structure that explains the data well. And this low-dimensional structure can be used to perform tasks like visualization. We can perform estimation because data is much simpler, usually, than one would expect since it lies in a high-dimensional ambient space. The low-dimensional structure allows us to perform feature extraction. And finally, what most of us are interested in is perform scientific discovery using this type of structure. And so first, I will go over some common structures that you've probably seen in numerous talks. And then I will focus on one particular type of structure that is simple enough yet provides intricate mathematical details and insights. So maybe most commonly seen structure in recent publications, at least what I read, is regarding high-dimensional regression. And in this context, the structure that we take care of is sparsity. Thanks. Thanks a lot, Akshay.
Oh, is that what happened?
I don't even make full screen. OK, so in high-dimensional regression, we often collect a large number of attributes, but only a few of those will be important for our prediction task. And furthermore,
when I click this, it goes away.
Yeah.
What the talk goes away.
Yeah.
Okay. So I shouldn't click this. Okay.
Thanks. So.
I think it's plain.
Yeah, it seems like Mac is much better.
Don't put it on the slideshow. Just put it on the full screen mode.
OK.
Go to view. Enter full screen.
The last one.
OK. So in a high-dimensional regression setting, we observe a data matrix X and observations Y, which are related to the prediction matrix in a linear way. So we have inner product between a row of this matrix and the high-dimensional vector beta. And often, in this setting, it is assumed that beta has only a few non-zero elements. These are these guys here. And this portion of non-zero elements is much smaller than the whole dimension of the vector beta. And then we add some measurement noise to this inner product. And so in this setting, a lot of problems have been studied, particularly variable selection. How can we identify which components of vector beta are non-zero? We can do estimation if we assume that the set of non-zero elements is much smaller than the sample size. And we can perform prediction well. A different type of structure arises in multitask learning, where we have a problem that is related to the previous problem. But instead of seeing one vector of observations y, we now observe a matrix. So each column of matrix y is related to x in a linear way. And furthermore, we assume that the matrix beta is row sparse. So there are few rows that are non-zero in this matrix. And the goal is, again, to exploit this structure that we assume on the problem so that we can perform variable selection, that we can predict well, and that we can estimate well. Okay? So this is what allows us to solve these problems, because otherwise solving them is ill-posed. And maybe finally, or one additional structure that often arises in application is low-rank structure. So we could assume that the data matrix that we observe, or that the parameter of interest is a matrix. And this particular matrix can be decomposed using SUD, and only few eigenvalues or singular values of this matrix are non-zero. So again, there is some underlying low-dimensional structure that can be exploited. And this has been done in collaborative filtering, in feature learning, in multitask learning problems, and other problems. Okay? So there are other problems that we have been studied recently, including sparse PCA, robust PCA, manifold learning, which all assume different types of low-dimensional structure that are exploited in some way. And so in this talk, we are going to focus on a particular problem where we observe a data matrix. And the goal is going to be, how can we identify a weak signal that is block structured in this data matrix? There are many applications of this, but during this talk, we will focus more on theoretical developments. I'm going to mention applications in very briefly. So the outline of the talk is as follows. We will start with the problem of biclustering, where I'll explain what biclustering is. I'm going to talk about some computational methods that are solvable in polynomial time and their properties. We will complement these results with information theoretic limits. And then we will point out that there's a certain gap between what can be done with computational procedures and what can be done, what are information theoretic limits. And next we will study a problem of compressive recovery of block structured signals, where we will study problem of localization of a block structured signal using compressive adaptive measurements. Okay? So we start with the biclustering problem. So the problem is the following. It arises in a number of applications, and all of these can be simplified to following mathematical problem. We observe a data matrix Y. So this is a noisy matrix. It could represent noisy measurements of edges in a bipartite graph, or it could represent gene expression measurements in biological problems. But the underlying structure here is that after permutations of columns and rows, there exists a contiguous block of signal that is different from 0. So we have a large matrix that is of size n1 by n2, and there exists a contiguous block after permutation of rows and columns. We do not know what the permutation is, which is much smaller. It's of size k1 k by k2. So this could identify a community in this setting, or it could identify a set of genes that are affected by certain active substances in drugs. But many problems can be abstracted in this sense. And the goal is going to be, how can we identify which rows and columns index a signal that is different from 0? in this noisy matrix. Particular mathematical model we are going to consider is we will assume that we observe a matrix A, which is a rank 1, a sparse rank 1 matrix, plus a Gaussian noise. So you can think of U as indexing a non-zero patterns of left singular vector, index non-zero rows, or relevant rows in this problem, and non-zero columns index non-zero elements of vector V, index non-zero columns in the problem. And then we drown this matrix in noise. So the goal is to recover the support of U and V using different procedures. And we will investigate what kind of procedures are able to recover the support of vectors U and V. Okay? And so this is just a very simple mathematical abstraction, but we will still see that a number of interesting observations can be made by studying such a model. Okay? So is the mathematical model clear at this point?
No, you say U and V are vectors. And
Yes.
you say the two vectors belong to 0, -1, +1, whatever.
So this means that they are proportional to 0, -1, and 1. So each element is each element of this vector is proportional to -1, 1, or 0. So you can think of this elevation to be plus beta or minus beta.
My confusion is from your notation. If each element is that, so you probably treat some power information.
Oh, you're absolutely correct. I should have been more precise about the mathematical notation. To clarify the point, what we are interested in is we are going to study matrix where each element is plus or minus beta or 0. We can generalize this to looking at average element in a cluster, but that's not so crucial for the conclusions will not change. We can always substitute beta by average beta. Okay, are there any other questions? Yes?
So where's the block information?
I'm sorry?
Where is the block information?
So block information,
In the model might not find.
so the block information is the support of U and support of V.
Okay, so they are in blocks.
It's not necessarily in blocks. So after permutations of rows and columns, you can represent this as a block. If you have some additional information that is somehow magically you know about the problem you're studying, then you can incorporate this into the estimation, and the results will change. But we will study a problem where we do not know the ordering of rows and columns. Yes?
Do you assume the blocks to be disjoint to each other, or they can overlap?
So in this simplest case, we will consider the case of one block.
Okay.
And so then in case where you would like to,
There are multiple blocks. Do you assume that they can overlap, or they need to be disjoint?
during this talk, we will not consider multiple blocks. Yes?
I presume we can recover the intersection of the supports and the entire support itself. Is that?
You can, could you repeat the question? I'm sorry.
That you can recover only the intersection of the supports of U and V and not the entire support itself. Is that?
If I recover the support U and V, I will have the support of the block.
Or you want to recover the support of the block, not of U and V.
Right. Akshay?
So the unit norm is not correct. The entries are magnitude beta, so you shouldn't be dividing by root k1 or something, right?
I do not. So if U and V are
If I make U and V unit norm, then
beta,
these are beta over root k1, k2.
that's correct.
Do I want it to be like that?
I mean, it doesn't matter how you normalize it.
I mean,
I'm going to tell you exactly what we're doing. Okay. But right. So if these are unit norm vectors,
yeah.
then this is going to be the signal strength here is going to be beta over root k1 times k2, and that's how we're going to express the results. Okay. So you're one slide ahead of me. So, right, so we are going to express all of our results in terms of parameter mu, which is you can think of it as an average element in this matrix. So let's start with a simple observation. So given that our elements, the noise elements are Gaussian, a simple thing we can do is just threshold our observation matrix A. And so a simple observation is that the maximum norm, element-wise maximum norm of elements of noise, is proportional to this quantity. So the noise level times root 2 log number of elements in the matrix. So if we threshold our matrix of observations A at level tau, where tau is of this form, we can identify the block. So as soon as the quantity mu is larger than tau here, a simple element-wise thresholding is going to give us the correct bicluster. So this is a very trivial observation. So now the question is, can we do better than this? Can we somehow utilize the fact that we have a very structured signal, as we discussed previously, to do better than naive element-wise thresholding? OK, so let's look at the information theoretic limits for this problem, which are going to provide some insights. In particular, what we can show is that if mu over sigma, so this is our notion of signal-to-noise ratio, is on the order of log the number of elements in the matrix divided by k, then any procedure that is trying to recover the matrix is going to fail with constant probability. So in some sense, this is the information theoretic limit. We cannot hope to do better. We are not magicians. But on the other hand, we can achieve this bound by looking exhaustively over all possible clusters of size k1 by k2. So we can study a procedure, theoretically, that enumerates all possible clusters and computes a score for each one of them. So the score would be just the likelihood for that particular block, and outputs a block that has the highest score. So this procedure will succeed at this particular level. However, yes?
How do we find errors?
Error is exact recovery. So we're looking at 0-1 loss. We either succeed to recover the cluster or we fail. But one observation is that this error is proportional to Hamming distance. So the Hamming distance would be bounded by k times probability of making an error. Right. But there are other notions. We could think of L2 recovery and like in the denoising setting. But we are interested in recovering of a block for scientific purposes, say. So just to recall, in the absence of structure, if we don't assume any structure in our signal, we can do our signal-to-noise ratio needs to be on the order of root log n1 times n2. So given that we do have structure, we can improve this by 1 over root k. And if you know by somehow that you have additional ordering of the information, so you know where exactly, you know that these things are ordered correctly so that you're looking for contiguous block, then you can do 1 over k better than no structure. Okay? So this is what information theoretic limits give us. And so one question is, can we do better than element-wise thresholding? Because there is a huge gap between what information theory gives us and what a computationally feasible procedure gives us. And so to study maybe something that can identify the block cluster, we are going to look at the singular value decomposition problem. So the way we wrote the problem earlier, we saw we're looking for rank 1 matrix plus noise. So maybe we can recover the rank 1 part using a singular value decomposition. In particular, we are going to look at the sparse singular value decomposition problem, which is to maximize this quantity subject to constraint that left and right singular vectors are sparse. This is, again, not computationally tractable problem to solve. So one approach would be to use a convex relaxation that was proposed in Alex Dasperman's paper with his co-authors. So the idea is we are still maximizing the trace between matrix A and an outer product between U and V, now in a lifted space. We're going to put an L1 penalty instead of looking at the L0 constraints for that matrix. And then they are subject to the following constraints. So if parameter lambda is equal to 0, then this problem would recover the rank 1 matrix U times V in a low-dimensional setting. So since we're in a high-dimensional setting, we need to impose some restrictions on the matrix X. So we are looking in particular to sparse matrix X that is of rank 1. So we are proposing, well, not we. We are going to study the proposed procedure for identifying a low-rank sparse matrix X. So what we can say about this problem, that if a solution is rank 1, then we have the following decomposition. And we can look at how well does the support of U hat and V hat recover the true unknown supports of U and V. So in particular, we have the following result that says that the singular value decomposition succeeds in recovering the support of U and V if signal to noise ratio is larger than this quantity. So again, we see that this computationally much more challenging procedure than element-wise thresholding still requires the signal to noise ratio to be quite high. So we haven't done much better than element-wise thresholding. And so one complaint here may be that we haven't thought hard enough about studying this procedure. Again, this is just an upper bound for the singular value decomposition. But we have a matching, not quite matching, but we have a lower bound that matches up to logarithmic terms that says that singular value, sparse singular value decomposition is not going to be of rank 1 with high probability if the signal to noise ratio is much smaller than this quantity. So in some sense, this particular procedure will fail for the problem of recovering a bicluster unless the signal is very strong. But if the signal is very strong, then a trivial element-wise thresholding will work. Okay. So here are some remarks with respect to the first part of the talk. So in particular, the sparse singular value decomposition does not seem to perform much better than the element-wise thresholding. In some sense, it works better, but these improvements are only in terms of constants. This will be shown in the simulation study in the next slide. And furthermore, there was a recent paper by Ma and Wu from UPenn and UIUC that shows for a different problem of detection, so testing whether beta is equal to 0 or not equal to 0, that no computational procedure can achieve the minimax rate unless the size of a bicluster we are looking in our alternative space is quite large. So we are looking at k being on the order of p 2/3, and in that setting we can detect. And so since localization, the support recovery of U and V is a harder problem than detection, there is a still open conjecture that this is also the case for localization, that unless we have large bicluster, no computationally tractable procedure will match the information theoretic limit. but that still needs to be shown. So in terms of simulation studies for element-wise thresholding, if we plot the signal strength, which is normalized with respect to the sample size, then we see that overall problem size is our procedure, our theory explains what's happening with the theory. So we see the transition from failing to recover the bicluster to a setting where we fully recover the bicluster. So in particular, here we are plotting the signal strength divided by root n1 and 2. And this is on our x-axis. And then we see that there's a transition into from not being able to recover. And from our simulation, we see that there are some constant improvements for the sparse singular value decomposition procedure. But these are not rate improvements, because again, we can see certain thresholding behavior around this region for SVD to be able to, between not being able and being able to recover the support. Okay. Okay, so are there any questions regarding the first part of the talk? Yiming?
Actually, from why do you focus on SVD or sparse or not? SVD really is trying to find the linear combinations of the original dimensions for axis. But your problem is really the subsetting problem, two-dimensional subsetting problem. So it seems SVD is not even an intuitively good choice as a solution. So I guess I hear what you're saying, but I just don't know why this is an important thing to study.
Well, so there are a couple of questions that you're asking. First, why did I choose to present element-wise thresholding in sparse singular value decomposition? We have tried other procedures, for example, looking averages of rows and columns, and a number of other procedures that people have proposed to study biclustering. So biclustering has been studied in an applied setting for many, many years, probably from before 2000.
I'm familiar with the biclustering problem, but you have a specific version of biclustering.
Right. So I have a simpler, much simpler setting.
Choose a subset on x and y, the two-dimensional space. So in that problem, I don't think it seems the singular value is in the wrong direction.
Well, I'm not quite sure that is the case, because if we see, so you may ask a question whether our model that we choose to study reflects application setting. So in particular, we are interested in, we have a data model A is equal to rank 1 matrix plus noise, where these U and V are sparse vectors. So you may argue that this is a very naive model for biclustering. But if you are willing to say that this is maybe a first step to solving what people care about in applications, then in this setting, singular value decomposition is trying to recover the strongest component in this data matrix, which should be rank 1 that is sparse plus noise. So one would hope that if signal is strong enough, you should be able to identify set of rows and set of columns from the singular vectors. And that is our intuition why we care about studying this problem. But I mean, I agree, we can look at a number of different procedures and we could study them. We chose to study 3 procedures.
Okay, I'm not here, just a comment. So I think you can move on.
Okay. Actually,
If I don't relax the sparse SVD,
yes?
can you analyze the performance? And what-
Yeah, then it's just exhaustive search.
So it's optimal.
Yeah.
Okay.
Just one random idea. What about having two-step idea, like first threshold and then do sparse? Threshold not that level of noise, but like a weaker thresholding and then using sparse speed. Because in last or some procedure like this for variable selection, sometimes it's possible that's why not doing lasso, but lasso and then doing another thresholding or changing the regularization coefficient of lasso, adaptively, we get better results for variable simulation.
That is definitely a valid point. So my conjecture is that that will probably improve maybe constants. It's unclear whether that would improve the rate significantly. Now, this relates to the comment that most likely achieving information theoretic limits at the rate of when k is on the order of root 10, there should be, the conjecture is that there is a gap between what the computationally feasible procedure, no matter which computational procedure, and information theoretic limit. So that said, maybe in practice, when the signal is larger than information theoretic bound, that may perform better than these two methods that we studied.
So the gap is like square root of k, right?
Right. Okay. So in the second part, I'll talk about compressive recovery of block structured signals. So during the first part, the setting was like this. We have a bunch of measurements which are arranged into a data matrix. And there exists a subset of these sensors that are block structured after permutation. But in many cases, we don't have to measure the whole matrix. So measuring n1 by n2 measurements, in the case of images, this would be, if I have a 1,000 by 1,000 pixel image, this would be 1 million measurements. So maybe we can do something better if we use to compress our measurements at the data collection procedure. And so in signal processing, we can create devices, or engineers are able to create devices that will collect measurements by taking inner products between a sensor and some random matrix commonly. And so this has been explored a lot. So this is an idea that has appeared as compressed sensing. So the idea is that instead of directly observing A plus noise, we can get to see M measurements from the model yi is equal to inner product between signal A, some random matrix X, and the noise. And so usually this quantity M, the number of measurements that we need to take, will be much smaller than 1 times n2. Okay? So what are the common choices for these measurements xi? Usually we take random measurements that satisfy certain energy constraint. Or we can choose them sequentially so that xi is a potentially random function of previous measurements. And so we are going to explore these two settings. So what this relates to is the area of compressed sensing. In the simplest case, this can be described as follows. We have some matrix X, which is random. Each row of this matrix is a random draw from Gaussian ensemble, say. And we have a sparse signal, beta, which we would like to recover. And so there are a number of ways how we can recover the signal. Again, we are going to focus on the support recovery. And what is known about this problem? So in the simplest case, where we assume that each non-zero element of vector beta is equal to beta min, then usual convex relaxations like lasso or Danzig selector require beta min over sigma to be on the order of n log n divided by m. So n is the length of a vector, and m is the number of measurements. And so this number of this signal to noise, this is the lower bound. So if the signal to noise ratio is on the order of n log n over k divided by m, then any procedure will fail with constant probability to recover the support of the signal. So these two results together show that compressed sensing works at its optimum, more or less, up to log K factor. Furthermore, if we choose our measurement sequentially, so we choose one x, we observe yi, then choose next xi. That depends on what we've observed previously. So this is in machine learning known as active learning. Then no matter how cleverly we choose these measurements, the signal-to-noise ratio needs to be on the order of √10 over m. So this is a lower bound. And furthermore, this can be achieved up to log factors using something like a generalized binary search. Yes?
So in the previous slide, are you assuming here like the sparsity can be order n or something? Shouldn't there be a sparsity? I mean, that n should be the sparsity.
Well, you need some condition on m that they don't explicitly write. So m should be depending on the size of how many.
Yeah, but it seems like that first leading n should be s. It should be like root of s log n by n, so that if m is at least s log n, then you'll return to.
Not really. So depends how you write this. So the average beta hat minus beta, like average L2 loss, is going to be on the order of s log n over m. But this tells you we are interested in a different problem. We're interested in support recovery. So here what I should write is that m needs to be larger than k times log n. And furthermore, look at how we, the way we standardize the noises that we are looking at the problem where x is, energy of x is on the order of 1. So what you are thinking of is that x is, if this is equal to n, then you would have a different result. So that also depends on the normalization. Okay. So back to our problem where we're trying to recover block structured signals from compressive measurements. What we are going to assume is a very simple setting where we know the ordering of rows and columns. So unlike the biclustering problem, we're going to assume that we know that we have K2 contiguous columns and K1 contiguous rows, which index the signal. Then we are going to look at the procedure where we take inner products between our signal and a random matrix, sequentially not designed. And we are going to further simplify a setting where we're going to assume that every element here is equal to mu for the purposes of this talk. So again, we're going to look at what happens when xi are independently distributed according to multivariate normal with which are scale like 1 over n1 and 2 so that we satisfy the energy constraint. In this case, we have the following result, that the signal-to-noise ratio is of the order size of the matrix divided by m times these two terms that I'm going to explain in a moment. Then we can identify the support beta hat by exhaustively solving this procedure. So we compute the likelihood for each beta. We fix a b. For each b, we solve the least square problem. And then we output beta hat that minimizes the loss. Okay, so this can be enumerated since we assume that the signal is contiguous. And then the lower bound can be shown by constructing difficult ensembles. And these difficult cases that we use to construct a lower bound are the following two settings. So this bound here comes from the fact that it is hard to distinguish two blocks that overlap except for one column. So suppose I give you two potential signals, and you have to distinguish whether it's one or the other. And these two signals overlap except for one row. Then you would need this many. Well, this gives you signal-to-noise ratio so that you can identify which one of these two. The second part comes from a different setting, where we have a large number of non-overlapping blocks, and we have to decide whether the signal is being generated by one model or combination of mixture of all the others. So these are the two extremes that give rise to the following lower bound. So the next question is, can we do much better than this lower bound by incorporating sequential measurements? And for sequentially designed measurements, we have the following result. So if the signal-to-noise ratio is much smaller than this, any procedure will make an error, no matter how cleverly the measurements are designed. And we also have an upper bound, which matches the lower bound up to logarithmic factors. And this I'm going to describe next, how we actually construct the procedure that achieves this lower bound. So there's maybe one remark worth mentioning here is that the upper and lower bounds for the case when we have structure and when we can use the measurement sequentially, there's a huge gap between having structure and not having structure. So in particular, this is the bound for the structured case. This is the bound for the structured case with random measurements. And here we had this kind of bound. So there's an improvement of 1 over k, again, that we can utilize, that we can achieve because of the structure of the problem. Furthermore, there's an additional improvement to be had by sequentially designing the measurements. Again, this is going to hinge the measurements we can design sequentially because there's an additional structure in the problem that can be exploited. So the procedure we develop is based on binary search. So effectively, what we do is we can proceed in 2 steps. So in the first step, we can study rough localization. So we can roughly identify where the block of K1 by K2 activation lies. So we identify a block of size 2K by 2K, which contains with high probability the block of activation. And then in the next step, we proceed again with the binary search-like procedure to identify exactly where within that larger block the true block lies with high probability. So this probably relates to your idea that if we split into 2 steps where we would use lasso in the first setting and then something better in the second setting, maybe we can do better. So in this setting, we actually can prove that this achieves the lower bound. But that is not the case with the biclustering, likely. And so the reason why that is the case because the class of models that are considered here is much, much smaller. We can actually enumerate all possible n-squared positions of k by k blocks in a data matrix. OK? And so for interest of time, I can talk about these 2 procedures afterwards. But let me show you in a simulation study. What is important here is, again, the plots similar to the ones we saw earlier. First, we observe a threshold behavior if we rescale the signal-to-noise ratio according to our theory. So if the signal-to-noise ratio is rescaled, then we can see that for all problems, there is a transition behavior from failure to success. And further, the point here is that for the sequentially chosen procedures, the signal-to-noise ratio needs to be much smaller in order for us to recover the support of the signal. Okay. And so I will conclude with a few things. So in this talk, we discussed minimax characterization of signal strengths that are needed for us to recover the support of a signal. We discussed both passive and active measurements. Contrary to what is known in compressed sensing, where the results are matching up to logarithmic factors. So there's only a log factor gap between what can be done using sequential procedures and passive procedures. If there's an additional structure, particularly here we assume that the signals are put in a rectangular, then huge gains can be had. And so I think the most important question that I have is what other types of structured signals can be exploited to identify the support or perform denoising or have improvements in different types of losses. And so I think actually had some work along those lines where they study graph structured normal means and characterize the generalization, I think, the denoising problem in that setting. But it's not clear whether this can be exploited also for sequential design, etc.
It can.
It can?
Yeah.
And what are the improvements? Do you gain constants?
Not much.
Not much.
Yeah.
OK. Well, maybe there are some signals with more structure than arbitrary graph structured signals that could be used to improve the results. Okay. So with that, I'll open to questions. Yeah.
It appears that we're not solving the original problem we're trying to solve with SVD or the element-wise threshold, because you are assuming that you are compressing the original clean signal and then inject certain noise, which is assumed to be Gaussian.
Mm-hmm.
Instead of compressing the actual noisy measurement, try to see something from it. So it's like the first half of the talk is not really comparable to the technique you proposed. Am I right? Or
It's absolutely correct. So we're not studying the same problem.
okay.
So the reason is that the point of the second part is that maybe an electrical engineer can design a measurement device that is going to output measurements of that form, which is to be contrasted with a setting where the measurements are directly observed. The sensors themselves are directly observed. And so these two assumptions are going to be appropriate for different problems. Are there any other questions? Okay, thank you.